Now, these observations are a result of the formation of charges. The charges found on the surface of the materials are caused by friction between the rubbed surfaces. The materials are said to be charged, and the study of these static charges is called electrostatics. Now imagine I take a balloon, it doesn't have any charge, I rub it on my hair to give it a charge. I can move it to a neutral object like a wall, and if I let it go, it will just stay there. Now if I take another balloon and I charge it in a similar manner, it should have the same charge as the first. And so if I hold them next to each other and let it go, it will be repelled. And so scientists speculated there are two types of charges called positive and negative charges. So an electric charge can either be positive or negative. If you have a neutral object, it will have an equal amount of each of these charges. But if it's a charged object like the balloon, then it will have differences in the number of charges. If it's a negatively charged object, it will have more of the negative charges, and if it's a positively charged object, it's gonna have more of the positive charges. Now let's say I bring two objects close to one another with unlike charges. What will happen? There would be an attraction force between the two. But if we take two objects with the same charge and bring them close together, they are going to repel. Now why did the balloon stick to the wall if the wall didn't have any charge? If you move a charged object next to a neutral object, what's gonna do, it will polarize the object. It can move some of these charges to one end and create a somewhat charged object. So an electric charge can either be negative or positive. So if we look at a neutral object, how many of these charges are we gonna have in there? An equal amount of each. Now let's say we take a charged object. We're gonna have more of the positive charges if it's positively charged. And if it's a negatively charged object, we're gonna have more of the negative charges. Now let's say we take two neutral objects, two balloons that we haven't charged, and we move them next to each other. What's gonna happen if we let them go? Nothing will happen. There will be no attraction between them because charges are equally distributed. Let's say we take two objects that have opposite charges, a negative charge on the left and a positive charge on the right. If we let them go, there will be an attractive force between them. Opposite attract. If you have two objects of similar charge and move them next to each other, when we let them go, there is repulsion. Same thing if they are both positive. What if we have a charged object on the left and then we have a neutral object on the right? See what happens as these come together? As I move the charged object towards the neutral one, what's going to do is polarize those charges. It's moving the negative charges farther away because they are being repelled by these negative charges. The positive charges are moving towards it, and thus there is an attraction between these polarized objects that used to be neutral. And so let's see this simulation. Take a balloon and move it around, and if I let it go, it stays where it is. But if I want to charge it, what I do is rub it on the sweater, and now I'm going to apply charge on the balloon. If I let it go, it goes back. Again, move it next to the wall and let it go, it moves back. So let's get a look at these charges. All the objects are neutral. They have equal amount of charges. But as I rub on the sweater, what I'm doing is pulling those charges off the sweater, and now they are on the balloon. The balloon now is negatively charged and the sweater is positively charged. Now see, when I move it next to the wall, it's polarizing the neutral wall. So I'm not doing any transfer of charges. Let's get two balloons and remove the wall. Let me add negative charges on this balloon and also add more on the yellow one. As I move that balloon next to the other, these are like charges, and so you can see they are repelling each other. All matter is made up of atoms, and although no one has yet found a way to get a closer view of an atom, different experiments have made it possible to build up a picture model of what an atom consists of. The colors in this model, of course, are used to simply distinguish between different particles. In the center of an atom is the nucleus. This is made up of even smaller or subatomic particles called the protons and neutrons. The protons each carry a positive electrical charge. The neutrons are as heavy as the protons but carry no charge. This means that overall, the nucleus is positively charged, and orbiting around it are negatively charged particles called electrons. The size of the negative charge carried by an electron is equal to the positive charge carried by a proton. The electrons are moving at incredible speeds around the nucleus. If we could pull an atom into its components, we would say that a neutral atom has the same number of electrons as protons. The force of attraction between the positive and the negative charges prevent the electrons from shooting off. However, electrons in the outermost orbits are weakly held by the nucleus and can be transferred easily from one material to another by rubbing. The material that gains the electrons becomes negatively charged, and that which loses the electrons becomes positively charged. Take note, however, that no charge is either created nor destroyed, it's simply transferred. A charged atom, positive or negative, is called an ion. A positive ion is called a cation, and a negative ion is called an anion. Charging by induction. Induction is the process by which a body acquires a charge of opposite sign without losing any of its own charges when another charged body is brought close to it. We can make a metal sphere be positively charged by bringing a negatively charged glass rod near it. The metal sphere, which is supported on an insulating stand, is initially neutral. We bring a negatively charged glass rod near it but without touching it. The negative charges, the electrons on the metal sphere, are repelled by the excess electrons on the rod and shift away from the rod. The charges can, however, not escape from the sphere because the supporting stand and the surrounding air are insulators. Thus, we see there is excess of negative charge on the side away from the rod and a deficit of electrons on the side nearer to the rod. These charges are called induced charges. What if the metal sphere is connected to the ground by a conducting wire? The negative charged electrons flow to the ground, whereas the positive charges at the near end remain due to the influence of the charged rod. Then we disconnect the sphere from the ground. The positive charge continues to remain on the sphere. If we remove the rod, the charges spread uniformly all over the sphere. Thus, we get a positively charged metal sphere. So again, here's the steps for inducing a positive charge on a metal sphere. If we wish to make the metal sphere negative, we bring a positively charged rod near it. Can you identify the charges on sides A and B? If you did this, then you're right. The electrons in the sphere are attracted to side A due to influence of the glass rod, while the positive charges are repelled to side B. What do you think will happen if we ground the metal sphere? Will the electrons flow from the ground to the sphere, or will the electrons in the sphere flow to the ground? Well, if you thought this, then you're right. If we ground the metal sphere, electrons flow from the ground to the metal sphere and neutralize the positive charges. Keep in mind that the positive charges never flow. If the earthing is removed, the electrons remain at A due to the influence of the positive glass rod. Upon removal of the glass rod, negative charges redistribute throughout the sphere. Again, here is a summary of the induction process. Charging by contact. This metal sphere is initially neutral. When we bring a negatively charged glass rod near it, the electrons are repelled away and the positive charges are pulled or attracted nearer to the glass rod. When the glass rod touches the sphere, electrons in the glass rod flow into the metal sphere enough to neutralize the positive charges, leaving only the negative charges. Upon removal of the glass rod, the negative charges redistribute within the metal sphere and hence it acquires a negative charge. Now imagine a positively charged glass rod is brought near a neutral metal sphere. The negative charges will be pulled near it while the positive charges will be repelled away. Upon contact, negative charges from the sphere flow into the rod, leaving only the positive charges. Upon withdrawal, the positive charges redistribute and the sphere is positively charged. Charging by separation. In this method, two metal spheres are brought in contact so that they form a single conductor. A charged rod is then brought near but not touching either of the metal spheres. Positive charges are attracted and remain in sphere A, while negative charges are repelled away and reside in B. We then separate the spheres while holding the charged rod in place. Negative charges in B redistribute, but the positive charges still remain in one end due to the influence of the charged rod. However, upon withdrawal, the charge redistributes. So we have two oppositely charged metal spheres. The electroscope. The electroscope is an instrument used for investigating the effects of electric charges and works on the principle of electrostatic charges. It consists of a thin gold or aluminum leaf on a plate connected to a metal rod that has a brass cap at the top. The cap acquires charge through induction or contact and spreads it through the rod to the plate and leaf. The cap is circular to ensure uniform distribution of charges on it. Both the plate and the leaf show the presence of charges by repelling each other, making the leaf diverge. The absence of charges is also shown when the leaf divergence decreases. The metal casing is for protection of the leaf from effects of drought. The casing has a glass window through which observations are made. The rod is supported by passing it through a plug of good insulating material such as rubber. The insulator stops charge given to the cap from spreading onto the case and leaking away. The casing may have terminal connected to the earth. When the electroscope is touched by a finger or connected to an earth wire, electrons either flow to the earth or from the earth depending on the charge on the electroscope. This process of losing electrons to or gaining charges from the earth through a conductor is called earthing. Now, this electroscope is called a gold leaf electroscope, and we have this conducting disc attached to this conducting rod, and attached to the rod at the bottom here is a thin gold leaf, and it's insulated from this metal box around it, so that if you place a charge on this conducting disc in steady state, that charge again will distribute within the disc, the rod, and the gold leaf. And so the gold leaf here then will be repelled from the rigid rod, and you can see here, this one, there is a scale so that you can quantify how much charge by how much the leaf diverges. So when a charged body is brought near the conducting disc, the leaf will diverge. Let's charge this rod. So you see, when brought near, long before we get close to the plate at the top, you can see a diverging of the gold leaf, and this is due to an induced charge on that leaf. And if you move the rod away, the leaf drops back to indicate no charge. Bring it back and there is divergence. But what I want us to do is to charge the electroscope, or transfer charges to the electroscope from this rod. After charging the rod, we bring it close, divergence. Take it away, it drops. But we can transfer this charge by touching the plate like this. And now we see that the isolated electroscope has a net charge on it, and that charge being positive, which is causing the positive charge on the gold leaf to be repelled from the positive charges on the rigid part of the conductor. And now what I can do is, if I touch it and form a path to the ground, I take those charges off the electroscope. So let's explain that. Here's a graphical animation of what happened. We charged the glass rod positive by rubbing it on silk. Then we touched the plate with a positively charged glass rod, and we observed that the leaves diverged, and this is due to similar positive charges. When we removed the glass rod, the leaves remained diverged. This showed that the electroscope is charged by conduction or contact. When the leaf was touched with the hand, we observed that the leaves dropped. That is, the electroscope is discharged. The leaves collapsed on touching the metal disc as the electrons from the earth flow into the electroscope and neutralize the positive charges. In other words, earthing took place when the electroscope was touched. An electroscope can be charged negatively by touching its disc with a negatively charged rod. When the plate is touched, leaves diverged due to negative charges being repelled downwards, and all the positive charges neutralized by the excess and negative charges. Another way of charging an electroscope is by induction. Now, if I bring the rod near the positively charged rod, and so there is positive charges at the leaf causing deflection. Now, if I bring my finger in and touch the plate, and then I remove my finger and then the rod, the leaf is left deflected. So again, let's explain that. Now, here's the graphical animation of what is happening in induction. The positively charged rod is brought close to the plate. Negative charges are attracted and get concentrated in the metal plate. The leaves acquire a positive charge because the glass rod repelled them from the metal plate. When the metal disc is earthed by touching, the leaves collapse because electrons from the ground neutralize the positive charges on the leaves. The negative charges on the metal plate are bound there as long as the glass rod is near the plate. When the glass rod is removed, the electrons redistribute and the leaves diverge due to repulsion. So the electroscope acquires a negative charge. In the same way, the electroscope can be charged positive by bringing a negatively charged rod near it. It repels the negative charges downwards, causing the leaves to diverge. Earthing causes the electrons to flow from the electroscope to the ground, leaving the positive charges. When the charged rod is removed, the positive charges redistribute, causing divergence of the leaves due to repulsion of the positive charges. Now, some of the applications of electrostatics include electrostatic precipitators and spray printing. Now let's look at electrostatic precipitator. Now, air pollution has become a serious environmental problem globally, especially due to heavy industrialization. Now, in an attempt to reduce the pollutants, some industries have installed electrostatic precipitators. Now, this is a smoke precipitator or an electrostatic precipitator. When it's turned off, the smoke flows through it, but when it's turned on, the air is clear of any visible smoke. The smoke particles collect in the plate cylinder instead. So how does it work? It has a metal mesh here that's charged with a high voltage negative charge, and there is an aluminum foil here that is charged to a high voltage positive. As smoke passes through the mesh, smoke particles pick up negative charges. The negatively charged smoke particles are attracted to the positively charged cylinder and stay there. Whatever is left exits at the top. Now, here is a close-up view of the smoke inside after it's charged. This candle doesn't give off much smoke, but when blown out, it does for a while. As you can see, there's enough smoke to go all the way up. I turn on the high voltage and do it again. This time nothing comes out at the top. Even with these two matches, but after a while of use, the aluminum cylinder gets dirty and has to be replaced. Next is the spray painting. The can is filled with the paint and its nozzle is charged. During spraying, the paint droplets acquire similar charges and therefore spread out finely due to repulsion. As they approach the metallic body, they induce opposite charges, which in turn attract them to the surface. Little paint is therefore used and efficient coverage of the targeted surface is achieved.
The battery, of course, is now 200 years old and was discovered, it is said, by a fellow by the name of Aloisio Galvani, an Italian. Galvani was in fact lecturing to some of his pupils. He was a lecturer in medicine. Mrs. Galvani was standing in the one end of the room, and she was preparing the evening meal because this was done at his home. And Mrs. Galvani was busy attentively listening to her husband, but also skinning the frog's legs. She noticed that when she touched the frog's legs, a twitch occurred. She called her husband over and said, "Have a look at this interesting phenomenon." And Aloisio Galvani came along, looked at the frog's leg, saw the twitch and said, "Wife, what a magnificent discovery I've made." Luigi Galvani wrote a letter to his friend Alessandro Volta. Volta was not a physician. He was what we would today call a physicist, or in those days they were known as natural philosophers. And what Volta did was decided to set up the experiment as Galvani had done, and realized very quickly that what had been discovered was not the essence of life, but some form of energy. And of course, this was electrical energy.